Hey everybody, welcome back. We're going to continue 12.1 in calculus with some examples of vector valued functions. So our first example, our function r of t will have an x component of 3, y is t, and z is t squared minus 1. The domain that t encompasses is the intersection of all the domains of the individual components. If we had square roots anywhere with t's underneath them, or something like that, we might have a restriction on our domain. In this case, t can go from negative infinity to infinity. And if I wanted to look at what's going on with in terms of x, y, and z, if I set y equal to t, notice I can substitute it in for t squared here. So z equals y squared minus 1. The x is constant. So what I did, I know how the parabola works. T squared minus 1 is down 1 at the origin, Well, in terms of the x equals 3 plane right here, down 1 is there, so that's my r0. I listed r of -1, a vector pointing to it, and this would be r of 1 right here. As time progresses, it's coming along like this, and it's sweeping out an orientation like such. So it comes underneath the x-axis and rises up. It's a parabola in the x equals 3 plane. If it helps, write out components, do them one at a time so you can see where the points are. This point right here, they're all 3 as the x component. It's not time dependent for x. So this point would be 3. Y is -1. That's what I use for my t. And z would be 0. R1 would be the same thing, but +1. And then here underneath the axis, this is 3, 0, and -1 for r of 0. Okay. Another example where I didn't draw the picture, but I just plotted the points is this function right here. And we'll show what happens as we're doing it live. So I've got r of t equals 3 cosine of t, 4, and then 3 sine t. Notice I made a table right here just because it's not as easy. The parabola one was a little bit easier for me to identify. I've worked with parabolas a lot, but when you're uncomfortable with where things go, definitely make a table. So my y value is constant here. So we are working in this y equals 4 plane. It's a nice little slice. And so I plotted the points. The point A, the starting point, or r of 0, is pointing to 3, 4, and 0. And then the next point it points to as we progress, it's coming up here like this, up to 0, 4, 3. So this point up here is r of pi over 2. And it goes around and it's doing a circle. The cosine and sine, this is it generates a circle. So it is doing something like this. It's going around like that and coming around like this. And if I went further, it should start coming back. But we are traveling along this circular path right here. It kind of looks like someone doing a lasso. The only part we wouldn't see in terms of it is this vector pointing to the points. So the actual only part of the curve that is present is this part right here. Okay. And it'll go back to it and I'll keep making circles. And it's not getting any further away. So even as we progress past 2 pi, it's starting to overlap. It's going in a circle. In this case, clockwise motion, if we look at it from the y end. If we look at it from the origin, it's going counterclockwise. So that's just a matter of perspective. Okay. So if we wanted to look at doing parametric equations of the lines, recall we had that. R equals R naught plus TV. We did this in chapter 11. We even found our V doing R1 minus R0. That's what we did. That's how we calculated. We subtracted endpoints. Well, now let's expand upon it. Let's just plug V in like that. And if we redistribute, we get R of T equals 1 minus T times R naught plus T times R1. This is just distributing T through and gathering like terms in terms of R naught. And we can see that from our vector here. The origin's right here. R1's there, R0. We did this line before. This is another way of doing it where we don't have to subtract the vectors first. We can just plug it right in. So let's see how our line segment kind of work in this situation. Again, we restrict T to generate line segments. But if we don't know what the T is, let's say we have the points. Let's just plug it in. So I'm plugging in my first point. We'll do a vector to that point. R0 is a vector from the origin to P. And then we'll do a vector from the origin to Q. 0, -4, and 3, and then 5, 2, 4. We are using that equation. We do some distributing and clean up. So I do that here. I distribute 1 minus T to each of those. And we get R of T equals 5T, 6T minus 4, and T plus 3. And you can see this is going to be when T equals 0 to T equals 1. That's how we set this thing up. So for any points outside of that V, it would be different time segments. Since we use those points to set it up, T is going from 0 to 1. That's kind of it for chapter 12.1. It's an easy section. It's short. We'll be doing 12.2 in a little bit. Peace.